Hi, Assalamualaikum. We are from Group 5 CDCS 2594A. We'll be presenting our group project, which is classification of mushroom dataset using backpropagation neural network. Here is our team members. We have Nur Husna Akila, Nurul Izan, Alia Fatini, and Aina Bahia. And here is our agenda, which include introduction, objectives, data analysis, comparison, and conclusions.
Good morning. So today we will be presenting our group project, which is classification of mushroom dataset using BPNN. So I will start with introduction. A mushroom classification is a critical task that involves determining whether a mushroom is edible or poisonous based on physical attributes. The task can be extremely valuable in ensuring the safety of food consumption and aiding in ecological studies. Traditional methods of classification rely on expert identification, which can be subject to human error and inconsistencies. The mushroom classification process is typically slow, especially when dealing with large datasets or unknown species. The main advantage of using machine learning for mushroom classification is its ability to automate the process, making it faster, scalable, and more reliable. Machine learning models, particularly those based on supervised learning, can use attributes such as cap shape or the to classify the mushroom accurately. Okay, next one, we move on to the objective. The primary objective of this project is to build a machine learning model that classify a mushroom into two categories, which is edible and poisonous. The edible is safe to consume and poisonous is potentially harm if consumed. And next is to develop a neural network classifier using the backpropagation algorithm. Then to evaluate the performance of the models, which is model accuracy and confusion metrics, will be analyzed to determine the model ability to classify the mushroom correctly. That's the objective. All right, now, so we move on to the problem statement. The problem addressed in this project is the classification of mushrooms as either edible or poisonous. So the mushroom dataset used contains several attributes such as color, size, shape, and gill attachment. By utilizing machine learning algorithms, we aim to create a model that accurately classifies mushroom based on these features. This project seeks to solve the following key challenges, which is inconsistency in human classification. While relying on human expert to classify mushrooms can lead to inconsistency as different evaluators may have very varying opinions or fail to spot certain characteristics. We have various of expert, we have various opinion from the expert. So this machine learning will help to solve those problems. Okay. Then efficiency in decision making. Machine learning models can process um, large amounts of data in a fraction of the time it would take a human expert, improving overall decision-making speed and productivity. As for now, we know that human expert could not really do the big data. So this machine learning will help to classify the big data. Okay, so let's move on to our next data analysis. This is our dataset information. We have 8,124 dataset number of instances and then 115 number of features. And our target class is either edible or poisonous. So it's just one neurons. And then our associated task is classification. Our dataset include these attributes. We have like 22 attributes, including cap shape, cap surface, cap color, bruises, order, and then it's also includes stock root, stock surface, veil type, veil color, ring number, and then so this is our BPNN diagram. We have 115 nodes for input layer, and we have 11 nodes for hidden layer, and then we have one node for our output layer. So the output of is the classification of mushroom as either edible or poisonous based on various physical characteristics using the data collected.
Hi, Assalamualaikum. My name is Nurul Izan. I will explain data pre-processing steps and then describe the neural network parameters and hyperparameters that we use. And I will go through a little bit about the coding. We use Google Colab to build our project. So first we upload the mushroom dataset, which is aggregate biota data into Google Colab, and then we import the necessary Python libraries such as pandas for data manipulation, NumPy for numerical operations, and matplotlib for plotting graphs. For the next step, we check the missing value, specifically the question mark, which indicates missing data in this dataset. And we notice the stored root column have 2480 missing value. So we replace the missing value with its mode, the most frequent value, and after replacement, we recheck to confirm there were no missing value. So the output for the stored root column, there is no missing value anymore. Done. Next, we drop useless column. We drop the val type column because it had only one unique value, which is p, and provided no useful information for the model. And after that, we rename the column recess question mark to recess to make it easier to handle programmatically. And then we use one hot encode categorical data because all features are categorical. So we use one hot encoding to convert each category into its own binary column. For example, for the column cap color with 10 possible value become 10 binary columns. And next, we also map target variable, which is class. So the value edible become 1 and poisonous become 0. And finally, we convert to NumPy. We convert both the input features and the target variable into NumPy arrays to fit into the neural network. And next is initialize parameter. Parameters are the value that the model learns automatically during the training. They are adjusted by the backpropagation algorithm to minimize the loss on the training data. So in our neural network, the parameters include weights and bias. For the weights, we have W1 and W2, which is W1 between the input and hidden layer, W2 between the hidden and the output layer, and biases. We have two bias vectors, B1 for the hidden layer neurons and B2 for the output neuron. So at the beginning of the training, we initialize these parameters with the random values or zeros for the biases, but then during the training, the model updates them to fit the data. For hyperparameters are the setting that we choose before training the model, and this control how the training happens, and we have to decide their values based on experiment. For the neural structure, uh, we set we use one hidden layer, and we use 11 neurons in the hidden layer because too few neurons might not capture the patterns in the data, which is underfitting, and too many neurons might overfit the training data or waste the resource. So through experiment, we found 11 neurons gave a good result. And then for the activation function, we choose the sigmoid function because it outputs values between 0 and 1, which makes it ideal for binary classification. And for the learning rate, we tested several values such as 0.1, 0.01, and 0.05. And for the number of epochs, we tested 500, 1000, 1500, 2000, and 2500 epochs. And for the weight and bias initialization, we initialize weight from the range negative zero point 0.1 and until 0.1. And for the bias, we initialize to 0 because random weights prevent all neurons from learning the same thing, and keeping weights small avoids saturating the sigma activation function. Bias start at 0 and are adjusted during the training. For the test speed ratio, we tested two ratios, which is 80% and 70%, because we want to test the model generalization ability with different amounts of training data. And then finally, we set a maximum allowable loss at 0.001 because if the model achieve very low loss early, we stop training to save time and to avoid overtraining. Here are the coding for the shuffle and setting the test speed. In this coding, we use 80% for training and 20% for testing. This is the coding for the activation functions. We use sigmoid function. And this is the coding to initialize parameters and to initialize weights and bias. In this coding, we initialize the learning rate 0.1 and epoch 500.
Assalamualaikum and a very good day. My name is Aina Bahia. So next we will go to the coding for the neural network. The first thing we did is that we create lists, which is the loss list, the accuracy list, and the test accuracy list to track the progress. And then we determine the max error of the model, which is 0.001, so that when the model reaches this error, it will stop because it means that the model has been doing greatly. Since we want to repeat the epoch, we use looping for this coding for epoch in range E. So for Z1 is the result of multiplying the features with its weights, and also we add the bias, and then we apply the sigmoid we can so that the output on the hidden layer can be normalized, which means that it will not be too big or too small. And then for the next one, which is the second layer, from the hidden neurons to the output layer, we also did the same thing, which is we multiply it by the weights and also add the bias, and also we applied sigmoid. So A2 is the result whether that can determine whether the mushroom is edible or not. And then we calculate the loss by computing the binary cross entropy loss function, and then we add it into the list of the loss list, and append the list. This is to calculate how wrong the model is and can track the progress by appending the list. And the next thing is we also check the training accuracy for each epoch by using the formula, and then we append the list of the accuracy to track the training accuracy for the epoch. It is done by comparing the prediction with the real answers. The prediction is the Y predict train, and the actual train is the real answers, the Y train. And just like I said just now, we save it in the accuracy list. And then we do the testing for the model, which is we use the same coding as before by multiplying the weights and adding bias, and also applying sigmoids to the function, and comparing the testing results to the real answers. And then we add it in the test accuracy list to track the progress. And also for the backpropagation, we calculate the error, and then how much that the weights that needs to be adjusted for the second layer and also the first layer. And lastly, for the epoch, we update the weights and the biases, and also we print the progress for each epoch. We also printed the final training and test accuracy, as well as the confusion metrics for the model. And lastly, we also plot the graphs, which is the graphs of training loss over epochs, and also the training versus test accuracy over epochs using matplotlib. So for the results, we go over the 80% speed percentage first with the learning rate of 0.1 and also the epoch of 500. So the final training accuracy is 97.32% and the final test accuracy is 97.54% with the precision of 0.9697 and the recall of 0.9835 and a as well as the F1 score of 0.9766. So you can see at the graph the training loss over epochs. So the loss has reached below zero point 0.2 at the epoch of 400, and also the accuracy has reached more than zero point 0.9 at the epoch of 100 and above, and it almost reached 100% accuracy at the epoch of 500. So next we add more epoch, which is 1000 epoch for the learning rate of zero point 0.1. The final training accuracy is 98.40%. The final test accuracy is 98.65%, which is high with the precision of 0.9802, recall of 0.9941, and the F1 score of 0.9871. So after around 800 epoch, the training loss has reached below than zero point 0.1, and for the training and test accuracy, it almost reached 1.0 after 600 epochs. So for the next one, we add more epoch, which is 1500 epoch for the learning rate of zero point 0.1. The final training accuracy is 99.05%, and the final test accuracy is 99.02%, with the precision of 0.9871 and the recall of 0.9941, as well as the F1 score of 0.9906. So for the same learning rate, we did the epoch of 2000. The final training accuracy is 99.63%, and the final test accuracy is 99.69%, with the precision of 0.9953, recall of 0.9988, and F1 score of 0.9971. And then for the epoch of 2500, for the learning rate of zero point 0.1, the final training accuracy is 99.78%, the final test accuracy is 99.75%, with the precision of 0.9965, recall of 0.9988, and the F1 score of 0.9976. So you can see on the graphs, the training loss as well as the training and the test accuracy over epochs has reached constant after around 2000 epochs. And then we use the different learning rate, which is zero point zero 0.01, with the epoch of 500. The final training accuracy is much lower, which is 51.72%, and the final test accuracy of 52.12%, with the precision of 0.5212 and recall of 1, and F1 score of 0.6853. For the epoch of 1000 at the learning rate of 0.01, the final training accuracy is 72.06%, and the final test accuracy is 72%, with the precision of 0.6506, recall of 1, and F1 score of 0.7883. On the training versus test accuracy of the epoch graph, we can see that it has increased significantly after the 800th epoch. For the same learning rate of 0.01 with the epoch of 1500, the final training accuracy is 89.98%, and the final test accuracy is 89.54%, with the precision of 0.8328, a recall of 1, and the F1 score of 0.9088. So on the accuracy graph, we can see it is starting to reach a constant. And then epoch 2000 for the learning rate of 0.01, the final training accuracy is 89.38%, and the final test accuracy is 88.86%, with the precision of 0.8310, recall of 0.9870, and the F1 score of 0.9023. So you can see on the accuracy graph, it has reached constant after around 105,000 epochs. And the next one is the epoch of 2500. The final training accuracy is 89.37%, while the final test accuracy is 89.11%, with the precision of 0.8384, recall of 0.9799, and the F1 score of 0.9036. And then we try a different learning rate of 0.05, starting with the 500 epoch. Final training accuracy is 89.40%, and the final test accuracy is 89.17%, with the precision of 0.8385, recall of 0.9811, and also F1 score of 0.9042. So in the graphs, we can see that the accuracy has reached constant after 300 epochs. Then, for the epoch of 1000, the final tuning accuracy is 97.34%, while the final test accuracy is 97.54%, with the precision of 0.9697 and the recall of 0.9835, as well as the F1 score of the 0.9766. For epoch 1500, the final tuning accuracy is 98.09%, while the final test accuracy is 98.34%, with the precision of 0.979, the recall of 0.9894, and the F1 score of 0.9841. So in the graph, you can see that around after 1200 epochs, it has reached a constant. For epoch 2000, the final training accuracy is 98.40%, while final test accuracy is 98.65%, with the precision of 0.9802, the recall of 0.9941, and the F1 score of 0.9871. And lastly, for the epoch of 2500, for the landing rate of 0.05, the final training accuracy is 98.63% and the final test accuracy is 98.65%, with the precision of 0.9802, recall of 0.9941, and the F1 score of 0.9871. And the next one, which is the 70% percentage split, I will pass it to Husna.
Okay, next for the results of 70% split percentage. This is the result for learning rate 0.1 and epoch 500. The final training accuracy is 97.40%, task accuracy 97.50%, and the precision is 0.9683, the recall 0.9854, and the F1 score is 0.9768. Now we move on to the next one, which is the higher epoch. For the same learning rate, 0.1, the epoch 1000, the final training accuracy is 98.38%, final task accuracy is 98.65%. Then the precision is 0.9796, the recall is 0.9954, and the F1 score is 0.9874. This is our graph for training versus task accuracy over epochs. We could see at the epochs 400, it's getting nearer to the 1. I think it's the 600 is getting nearer to 1.0. Okay, so the next one is the learning rate 0.1 for epoch 100 and 1500. The final training accuracy is 99.19%. The final test accuracy is 98.97%. The precision of it is 0.9856. Recall 0.995445. The F1 score is 0.9905. As we can see, the graph, it's getting, even after 600, it's getting nearer to the 1.0 accurate. All right, so next we'll move on to the learning rate 0.1 for the epoch 2000. The training accuracy is 99.7%. The final test accuracy is 99.71%. The precision 0.9954. The recall is 0.9992. And the F1 score is 0.9972. Okay, so this is the last one for the learning rate 0.1, epoch 2500. The training accuracy is 99.79%. The final test accuracy is also 99.79%. The precision is 0.9962 and the recall is 1.0000 and the F1 score is 0.9981. As we can see, it's getting more stable and constant even after 500 of epochs. It's getting nearer to 1, and for after the 2500 epochs, it's touched the 1 accuracy. Now we move on to the learning rate 0.01 for epoch 500. The final training accuracy is 51.09%. The final test accuracy is 53.45%. For the precision of 0.54345, recall 1, and the F1 score is 0.96966. Next, we go to the higher epoch for the learning rate of 0.01, epoch 1000. The training accuracy is 85.07%. The test accuracy is 85.97%, and the precision is 0.7921. The recall is 1, and the F1 score is 0.8840. This is the graph of training versus test accuracy over epochs. It's getting higher after the 600th epochs. Next, we are going to the learning rate 0.01, epoch 1500. The training accuracy is 89.71%, and the final task accuracy is the 89.91%. The precision is 0.8434, and the recall is 0.9962. F1 score is 0.9134. All right, so next is for the learning rate 0.01 equal to 2000. It shows that the training accuracy is 88.99%. The test accuracy is 89.50%. The precision is 0.8437. The recall is 0.9862. And the F1 score is 0.9094. The graph of the training versus test accuracy over epochs is getting higher after the 750 epochs. Next, we move on to the last one for the learning rate 0.01, which is the epoch of 2500. The training accuracy is 89.34% and the test accuracy is 89.66%. The precision is 0.8482. The recall is 0.9823, and the F1 score is 0.9104. So this is the graph, not much difference, but we could see that it's getting nearer to 0.9 as if it's reached the 2500 epochs. The next one, we go to the learning rate 0.05. First epoch is 500, which shows the training accuracy 89.34%. The test accuracy is 89.66%. This is the training versus test accuracy of epochs. We could see that after reaching like 300 epochs, it's getting more balanced, constant. Next is for the higher epoch for 0.05 learning rate, epoch 1000. The training accuracy is 97.40%. The test accuracy is 97.54%. The precision is 0.9691. The recall of it is 0.9854. And the F1 score is 0.9772. As you could see, the graph is a lot much different from before. But we could see that it's getting to it's nearer to 1.0 accuracy on epoch 1000. Next, for the same learning rate 0.05 epoch 1500, the training accuracy is 98.07. The test accuracy is 98.28. The precision is 0.9766, 0.99164 for recall, and 0.98404 for F1 score. This is the training versus test accuracy of epochs graph. It's getting more nearer to 1.0 accuracy when it's reached the 1200 epoch. Okay, so next is the epoch of 2000 for learning rate 0.05. Training accuracy is 98.38%, which is very high, and then the test accuracy is 98.65%. The precision is 0.9796, and the recall is 0.9954. The F1 score is 0.9874. As we can see on the graph, it's getting more constant when it's reached the 100 and 1500. 1500, 1750 is getting nearer to 1.0 accuracy. So for the last one is 0.05 learning rate. And for epoch 2500, the training accuracy is 98.61%, and final test accuracy is 98.73%. As we could see on the graph, it's getting more higher and constant after 2000, and it's getting nearer to 1.0 accuracy on 2500 epoch.
Hi, my name is Alia, and this is what we have compiled for the training results. First is for 80% split. So here you can see that the lowest accuracy we got is when using 0.01 learning rate with 500 epochs with the value 51.72%. And the highest accuracy that we got is using zero point 0.1 learning rate with 2,500 epochs with the value 99.78 accuracy. For percentage split 70%, um,
The highest is also when using zero point 0.1 learning rate and 2,500 epochs with a value of 99.79%. And the lowest is still using zero point zero 0.01 learning rate and 500 epochs. Moving on to testing results for 80% split. The lowest we got is 52.12 accuracy when using zero point zero 0.01 and 500 epochs. But the accuracy is the highest when using zero point 0.1 learning rate with 2,500 epochs with the value 99.75% accuracy. And for the 70% split, the highest accuracy is using the same linear rate and epochs, which is zero point 0.1 and 2,500 with accuracy of 99.79%. I will be continuing on the comparison of training sets. So as you can see in the orange row, it is for 80% split, and below it is for 70% split. In most cases, 70% split performed better than 80% split, likely because it provided more data for testing while still keeping enough data for training. And as the number of epochs increases, you can see that the accuracy also increases. For both percentage split, 80 and 70%, the highest accuracy is when we use learning rate zero point 0.1 with 2,500 epochs. However, 70% split overpassed 80% by zero point zero 0.01 accuracy. Moving on to the best test result. So by using the sigmoid function with 11 hidden nodes, the learning rate of zero point 0.1 and 2,500 number of epochs with 70% split is the highest accuracy that we get, which is 99.79%. So using zero point 0.1 learning rate, it gives faster learning compared to lower rates, and using the percentage split 70% gives the model to have enough data to learn patterns without overfitting too much, and enough data for training while still keeping a reasonable amount for evaluation. And for using 2,500 epochs, it gives more training cycles that help the model to converge better and improve accuracy. And also, as you can see from before, as the number of epochs increases, there is a possibility to get higher accuracy. So next, let's look into the advantages and weaknesses. So in this project, the advantage is that it gives effective feature learning, where the neural network could capture complex patterns in the mushroom attributes to make accurate classifications. And also, when we use manual implementation, it gives a deeper understanding of how backpropagation and neural networks work. While on the other hand, the weakness for this project is it is time consuming training because the number as we use higher number of epochs, it will increase the training time significantly, especially when we use 2,500 epochs. And also, lastly, it lacks scalability because as we use manual implementation, it can be less scalable compared to using advanced machine learning libraries like TensorFlow or PyTorch. So before we end our presentation, to conclude, in this project we used backpropagation neural network to categorize mushrooms data uh, into edible and poisonous ones according to their characteristics. And we obtain highest accuracy of 99.79% when we use zero point 0.1 learning rate, 70% percentage split, and 2,500 epochs, which we applied after we have cleaned the data, like replacing missing values and dropping unnecessary columns, and also testing out different settings. So this demonstrates the model's strong ability to learn complex patterns in the dataset. So all in all, the project shows the potential of machine learning in assisting real-life issues such as food safety by making predictions. So that is all for our presentation. Thank you so much.